Now, I think I told you I sent you a video. So if I just would like you to, for your next homework, you don't have to do this every time, but it would be a good exercise for you to learn a little bit about the R markdown. So, and I think I mentioned that I found a tool at the last minute, this tool here called MathPix. And it's quite nice because you can find, maybe you saw, but you can take an equation, for example, this equation, for example, and you can just copy it like this. And then it gives you this, which is, you can just paste that into our markdown and it'll give you kind of professional looking equation in there. And you can easily learn this, what's going on here. If you do this a few times, and you sort of take a look at it, you'll see how to do it, how to type a lot of it on your own. But the only thing is here they give you, I didn't realize if they give you like a limited use of this for free. So I think it's like maybe 50 or 60 or 70 times you can use it, maybe something like that, maybe 75 times, I'm not sure. So, and then they have a bunch of other stuff here. I don't know what this is, data, originals. You can do search. So this might be interesting. Let's try solver, see what happens. So it's trying to solve this equation. So it gives you solutions to it. It's kind of fun, right? You can also do this kind of thing, I think, in Microsoft OneNote. But anyway, so you get solutions for it. And see, you can see where it says SNPs remaining 40. I only have 40. And I don't know, what does search do? Oh, it searches on the web maybe or something to find something similar or examples and so on. That's nice. Okay, so this is a nice tool called MathPix Snipping Tool. And they make you sort of sign up for it, but you can do that. And then, so like, I would like it if you did chapter 10 using RMD, and it might, then you can knit it here, and I'd like you to knit it as a Word document. And also, I figured out finally, or maybe they gave new information in the error message, so it's not very hard to fix this, so that you can make PDF documents as well. You just have to install a particular package, which they tell you about. If you try to do it, you get an error, so you can install that package. I won't get that error now because I know which package it was, but you will find out in the error message. So when you hand it in, though, I'd like you to hand it in as a Word document, but you can also knit it in HTML. And if you don't get any errors, then it comes out as a document. And here's that, all the, pardon me, here's all the latex. That's what this MathPix was giving me the latex so that I could print out these as well. You don't have to use the latex if you don't want to, but I just wanted to test it out. Okay, so, and by the way, there's some options here. You can go to here, the settings, and you go to output options. And if it's HTML, you have certain options. So for example, there's a theme that you can choose. I didn't try this, so I don't know what the difference is in the different themes. And I guess you could actually use CSS. Now, if you want to have actual images in this file, you have to sort of treat it like it were a web page. So you have to have you have to know where this RMD file is, and then you have to put the images in that folder or subfolder, and I guess you have to reference the images. So if you actually want to have images, you have to treat it like it's a web page. I guess. Has figures here and advanced. So yeah, I don't know exactly what this theme does, and I don't know what this is, default highlighting. But you have some options that you can play with here. Okay, so for chapter 10, I'd like you to use RMG. You don't have to use, as I said, you don't have to use this so-called latex. This is latex. I remember when I was a graduate student in math a long time ago, and a friend of mine, a woman who was also a graduate student, and basically, maybe this is not fair, and it's not true either, but I don't know if she was such a great mathematician, but her teacher was a very good mathematician. He was writing a lot of papers, and he needed someone to, basically, write all the math equations well. And this is a long time ago, before they didn't have even Microsoft Word at that time. We didn't even have computers at that time, actually. So anyway, so she just had to learn LaTeX, and then she was, implementing it. I don't know into what. It wasn't into Microsoft Word, but it was into something, and so that his papers would be properly formatted and so on. And she just did a lot of that work, and she ended up with her PhD magically. No, I don't think it was. No, she was good, but I mean, I know she did a lot of work for her professor, her thesis advisor, her dissertation advisor. And it was basically this kind of work. So she had to learn text. It's called, what's it called? LaTeX, which I thought was going to be really hard, but I played with it here, and it's quite easy, actually. Not very hard, actually, at all. So these two lines here give you a line break. So I have a line break here, and then this equation z. So, and if you want to throw in some text, you have to use a backslash text, and then you can put a word in there as text. And so it's not that hard, actually, to do it. Okay, but you can learn it pretty easily by using that tool. You just look at what it did. There's not very much here, so it's not very hard. Okay, so let's go now to the book. And I'm going to, let's see, I guess we didn't finish chapter 9, but I mean, we didn't do chapter 9, but I'm not going to spend much time on chapter 9 because I think you can read it and it's pretty clear. But let's just breeze through it. So we have concept of vectors, and we can add them and multiply them. We have matrices, and we can think of a matrix like as a bunch of columns, and we can add matrices. We can multiply matrices like we did last time. We can do it in R. This says that we can take what the transpose of a matrix just means make the columns rows and rows columns. And if you do that twice, then of course you get back the original matrix. And this is a property that you can prove pretty quickly that shows that the transpose of this should be that. And we have to remember that AB is not the same thing as BA. Matrix multiplication is not the same as regular number multiplication, where you can take two numbers and switch the order. You still get the same thing. We have the dot product here, and that's important for the matrix multiplication. We have a function of a single variable output to a single number. And we also have function from many variables input, and the output is just one number, one value. And like the mean is actually that in R, right? You can put in a bunch of numbers into the mean, or you can just put one. So you can take a bunch of numbers and then you just get out one value for the mean. So that's actually that. And then we can talk about here, this, whenever you see a bold function name, that means it's the output is a vector. So in other words, we're talking about something like this, where you have one input, but you get two outputs. Okay, so you get a vector as the output, and we'll use a sort of bold F to tell us that the output is going to be a vector. So here, for example, suppose we have one input is t, but we're going to get a vector as the output. You can see that this is a vector. It's got one comma in there, which means that there's two elements to this vector. So one of them is x of t and the other is y of t. So here's an example where we have t. We can put in t, and both x and y will depend on t. So you can see that x is a function of t, and y is also a function of t. So for example, x might be 5t, so this function of x of t is 5t, and y might be just t. And so if we put in t equals something, for example, if we put in t equals 2, then when t equals 2, x will become 5 times 2, and y will become 2. So we will get x equals 5 times 2, which is 10, and y equals just 2. And then suppose that f is a function of x and y. So suppose it's this function of x and y. So when we put in x and y, we get this. And here we're saying that what we're getting out, you can see, is a vector. Okay, it has two components. So the first component is calculated as x minus 2, and the second component is calculated as x times y. So we just said that x became, after we put t equals 2, then x became 10 and y became 2, and then we calculate from here what the output is. So x is 10 minus 2, so we get 8, and y is 10 times 2, so we get 20. So when t is equal to 2, we get values for this because of these definitions, because x and y are both functions of t, and then f depends on x and y, and in this case it depends in this way on x and y, and we notice that f here is bold, meaning that we're getting as our output a vector, and this is the vector that we're getting, and we calculate it from the x and the y after we've calculated what x and y are from the t value. So we calculate what x and y were here, then we put those into here and here, like this and this, and we get 8, 20 out. So we see that when y is 2, we get out this vector 8, 20. So we might have x of t equals 2t and y of t equals t squared. So when you put those in here, you get 2t and t squared. But so when I've put in, for example, t equals 3 into here, then I get what? I get 2 times 2, I get 6, and I get 9. So I get 6, 9. So I get out a vector. So even though I just put in one value here, I got out a vector. So that's kind of different. And that's why I have this as bold, because I'm getting a vector as the output. So we're using bold like that to indicate that the output is a vector. And this is called a vector valued function. It just means the output is a vector. And we can have a function like this from R4 to R3. That just means we're going to have 3 pieces as the output. Here's one. Here's another. Well, here. And then the third piece. Whoops. So we have 3 outputs, or we have a vector with 3 elements as the output, and the inputs have this many. And we calculate the outputs by taking what's in here and doing this to it. Okay. All right, so that was that chapter. And now we go to calculus, a review of calculus, and more than just a review maybe. So this is just the definition of the derivative from calculus. And the idea is that if we have some curve that if we want to know how quickly the function is increasing, like here it's not increasing very much at all. As I move to the right, the height barely increases. But over here, as I move to the right, the height starts to increase. And then over here, as I move to the right, it's even increasing more. So we might like to know how quickly it's increasing, and that's like the slope, something about the slope. So that's the derivative tells us that. And we have there's so many different notations for the derivative because the derivative is such an important thing, and different people have used different notations for it, but they're all the same thing. They're just different notations. So we can write it like this, we can write it like this, we can write it like that, we can write it like this, and we can write it like this. Okay? Now, here's a rule from calculus that says if you have the derivative of f and plus g, you can, oops, there's a mistake here. Okay, so we have this rule here, it should be plus minus here. And so we can use it, for example, to find the derivative of this. So I'm sure you know how to do that. We also have another rule when we have a product of two functions. We have what's called the product rule. And then we have this one, which is the most important one for neural networks, and that is the chain rule. So that's when you have this is not the product of f and g, but rather this is put g into f. And then if you want the derivative of that thing, that is, if you want this, you have to do this. This is what you do. Now, there's another way to write that, and that is this. So this is another way to just another notation for this rule. So it says dy dx is dy du du dx. So that is the chain rule. And here's some kind of justification for the chain rule. Now we have, we look at the function e to the x. That's going to be very important for us. And the derivative of e to the x is actually really the easiest, maybe the easiest derivative, because you don't have to do anything. You just get e to the x back. So that's nice. And that will help us to find the derivative of this function. And this function is very important in neural networks. It's called a logistic curve. It's also called the sigmoid function, sigmoid curve, or sigmoid function. So you could call it the sigmoid function, or you could call it a logistic curve. Anyway, this is what it is, and we give it a special symbol, sigma, but that's the name of this function. But anyway, this is what the function is right here. So it's 1 over 1 plus e to the minus x. So that's a very important function, and the graph of it looks like this. So it's a sigmoid curve. It's called the sigmoid curve. And we need the derivative of it, but we won't actually use this. We'll do it a different way. But anyway, you can follow through these steps. They're actually quite easy. And you can show that the derivative is the original function times 1 minus the original function. Okay, let's keep going. All right, now the question is, maybe this is new. So if I ask you the derivative of this, you probably, I think everybody's had this subject before, and you could do that derivative pretty easily, right? That's not hard. But how about, oh, sorry, before we get to that. So, and then also, if I asked you to find the maximum or the minimum of a function, you probably remember that you normally want to take the derivative, right? So we have like, here's another example. Suppose we had a function and its derivative turned out to be this, just for example. Then what do we do with the function? Once we, like here, let's see, sometimes the equation of derivative might become, well, anyway, what do we do if we want to find the maximum or the minimum? We usually set the derivative equal to 0, right? But this function doesn't look like it's going to be that hard if we set it equal to 0 and look for the answer. It looks like, oh yeah, that's not going to be too hard. But actually, it's impossible. You can't find the solution to that, I believe. I hope so. That's what I said in the text. So then we're going to be stuck, right? So if we had this derivative and we wanted to find the maximum or minimum, we're kind of stuck, okay? So on the other hand, if you had this curve, it's easy to find the minimum. Right? You take the derivative and you can do it. Okay, so we want a different method for finding maximums and minimums. And this is critical. This is absolutely the most important part of neural network. So we can't, let's say we have this function as the derivative, and we can't set it equal to 0. So we can't find the lowest point or the highest point. So we want another technique. Instead of setting the derivative equal to 0, we have another technique called gradient descent. So how does it work? The method we will use in neural networks is called gradient descent. It's an iterative process. What does iterative mean? It means that it won't be done in one step. You're not going to do it in one step. Rather, we're going to just keep repeating something and getting closer and closer to the answer. So that sort of indicates that we may not get the actual lowest point, but that's may be good enough for our purposes. We don't have to get the actual lowest. We just want to be able to sort of move in the direction of the lowest. And if you have a driverless car, nothing works absolutely perfectly in the driverless car, but it works pretty well, right? You know that it works pretty well. So it means that they don't have the perfect solution, but they're minimizing their errors. They're getting closer and closer to 0 error. Now it's not perfect, so it's not 0 error, but the idea anyway is that it's done, instead of it in one step, we repeat something many times. Hopefully each time getting closer. In this case, we want to get closer to the lowest value. So like, suppose we were up here. We're standing, and think of this as a valley, like a mountain maybe up here, but here, this is a valley, and we want to get down to the bottom. What can we do? The idea is, I wish I had a good picture of this. I should have put a better picture in here. Gradient descent. And here, let's look at this picture, or maybe even this one. Let's try this one. Okay, so suppose we're up here and we want to get to the lowest point. So this is like we're standing on part of a mountain and we want to walk down to the valley. We want to get home. Okay, now, and it's dark out, and not only is it dark out, but we're blind. So what are we going to do? What are you going to do? Well, they say what you're going to do is you're going to feel with your feet. So you're going to stand, sort of standing on the mountain. You'll sort of move this way and move this way. And what are you going to be looking for with your feet? You're going to look for the direction down. So you'll see, oh, well, if I point this way, I'm going to go up. No, then you're not going to go that way. Right? So what are you going to do? You're going to find another direction and go down. Okay? And you're going to take one step down in that direction. And hopefully you're going to find the direction which is the steepest down. Part of it will be up, and part of it will be slightly down, and another part will be more down. So you're looking for the direction of greatest descent, and then you'll take a step, and then what will you do? You'll repeat the process again, right? You'll feel again, which direction should I go? And you'll keep doing that. And so hopefully maybe you'll get to the lowest point, which is your goal. That's called the gradient descent method. So the idea is still to get to the lowest point, just like with a derivative, right? Here you have a function, You set the derivative equal to 0, you get to the lowest point. You find the lowest point. We're still trying to do that, but we can't set the derivative equal to 0, so we can only walk in the direction of greatest descent. And when you take one step and then repeat, one step and repeat, one step and repeat. Okay? Now, when I say the direction of greatest descent, we're talking about derivatives there, right? Right? Because we want to calculate the slope. The slope here, that means derivative. What's the slope here? Maybe it's not so much, right? We have different slopes. So we're talking about derivatives still, but the thing we can't do that we could do here we had the derivative and we could set it equal to 0. Here we still have the derivative. We still can figure out what direction to go, or we can figure out what direction to go, but we can't set the derivative equal to 0 because we saw some equations don't do that. You just can't set it equal to 0. You can't find the solution to that. But you still have the derivative. It's not that you can't find the derivative, it's that you can't set it equal to 0. That's the problem. But we do have the derivative. We do calculate the derivative. And the derivative tells us which direction to go. So that's the idea of gradient descent. So that is the idea. Now, how do we do that mathematically? Not with our feet, right? Because we're not really standing on a curve. And we don't even, there is no, I mean, we're just going to have a formula for the curve. Now this, by the way, this illustrates one problem with this process. Because suppose you're standing at B, so you're going to go, okay, I should move down here, and then okay, I should move down here, and then okay, I should move down here, and okay, I should move down here, and then you'll stop, right? Because if you move again, you're going to be moving up, so you're going to stop. So you're going to find what we'll call a local minimum, but this is a lower point than this. So we say this is not the absolute minimum, it's just a local minimum. So that can happen with this process. So there are some tricks we could think of, maybe avoid that sometimes, but basically that's a problem. Okay, so now we're talking about, suppose we have this picture. So how many variables are involved in this drawing? We have 3 dimensions, or 3 variables. X, here's Z, so here, where is it? Here it is. So Z equals X minus Y squared, X minus 10 squared plus Y minus 15 squared. So how many variables are there? 3. So, okay, so that is different than derivatives before, because before we only had Y equals F of X. We only had 2 variables. Now we have 3. So how do we work with derivatives in that case? Because we said we want to find derivatives because we want to find slopes. But what does it mean in this scenario where we have 3 variables, not just 2? In calculus, that's called partial derivatives. Partial derivatives. So here's the same picture, or another picture anyway. Here's a picture, a 3-dimensional picture. What if I take this plane and I cut this, by the way, this curve, these kinds of curves are called paraboloid. It looks like a parabola, but it's 3-dimensional. It's called a paraboloid, okay? And this is also a paraboloid. Now, if I take this paraboloid and I cut it with a plane, a vertical plane, if I cut it with a vertical plane, what kind of object am I going to get? What's the intersection of a paraboloid, like this paraboloid here, and this vertical plane here? What's the intersection of those? A parabola. You can sort of see it here, right? It's here, and the other side goes down, and it's going to be a parabola. So suppose we have a function that can be drawn like this paraboloid here, and then we cut it like this. So we end up, like we just said, with a parabola. Now, do we know how to find the derivative of a parabola? Yeah, everybody knows how to do that. We know how to find the derivative of a parabola. Now, where is this parabola? Where is it located? In what plane is this parabola located? Where is it? It's in a plane. What plane is it? Because remember, a parabola has to be in a plane. It's only two-dimensional. So where is it? Which plane is it in? It's in this plane here. So this is a plane, and that's where our parabola lives. Okay, it's also in this paraboloid, but I asked what plane is it in, and it's in this plane. So let's say that we have this paraboloid, which I think is here. This is the definition for that paraboloid. So it's an inverted paraboloid here. It's upside down. And then we take a plane. Now, which axis is this? But it says the intersection of a paraboloid and vertical plane perpendicular to the y-axis. So this must be the y-axis. This must be the y-axis, and this plane is perpendicular to that. This plane is perpendicular to this axis. So this must be the y-axis, and then this plane is perpendicular to the y-axis. That means that we're saying y is equal to something. What's the equation of this plane? Suppose that this cuts through the y-axis at 3. So here you can see 1, maybe we can't see it. 1, 2, 3. Maybe it cuts at 3. So what would be the equation of this plane? So what do we want? We want to identify all points in this plane. And what do all points in this plane have in common?
3.
Their y coordinate is 3. So that's the equation of this plane. Y equals 3. That's the only restriction we need. And anything that satisfies that equation will be a point in this plane. This is, we can say this is the plane y equals 3. So, okay, now here's the equation of the paraboloid. Right? Which points are going to be on the parabola? Well, what are they going to be? They're going to be both in the plane and in the paraboloid. So to be in the plane, what do they have to satisfy? Y equals 3. So whatever else, we have to have y equals 3. So we can just substitute y equals 3 in here. And all of those points, anything with y equals 3 is going to be in the plane. And anything that satisfies this equation where y equals 3 is also going to be in the paraboloid. So if we want all the points on the parabola, we just take this and do what? Set y equal to 3. So that's what I did. I set y equals 3. Maybe I didn't. So what do you get for the equation of the parabola? Minus 3 squared plus 10 gives you what? Minus 3 squared is minus 9, plus 10 is plus 1. So the equation for the parabola is z equals minus x squared plus 1. Now, do you know how to take a derivative of that? So that is how we're going to take derivatives of functions with more than one input. What do I mean? That is, what do I mean? We're going to fix y at some value and then take the derivative of the simpler equation. Right? So that's what we did. We got z equals minus x squared plus 1, and we can now take the derivative of that with respect to x. And what's that's going to give us? What is that going to give us? That's going to tell us the slope of this parabola, right? Okay? But the thing is, we're going to be at some point on here, like here. We're stuck here on this point, and we want to go, let's say now, since it's an inverted paraboloid, let's say we want to go to the top. And we don't know which direction to go. Now we have the derivative of this parabola. Now we can tell in terms of if we're going to stay in this plane, we know what direction to go. We know that we should go up if we want to get to the top. But we're not necessarily limited to this plane. We just did that arbitrarily. So now instead of this plane, we could take a plane perpendicular to this axis. This is the x-axis. Instead of this plane, we could do the same thing, but the other plane. So we're here at this point. This plane will touch us, but we could also have a plane in the other direction that will also touch us. And so we could do the same thing then, and that will tell us more information about what direction to go. And then we can use like a blending of these two pieces of information to figure out what's the really best direction to go. And that's the idea of three-dimensional derivatives, or derivatives in 3D. So that's called partial derivatives. So partial derivatives are when you take a derivative in just one direction, like we did, just in the y plane, and then we'll do the same thing in the x plane. And each of those are called partial derivatives. And the notation is like this. So we don't use this notation when we're doing partial derivatives, we use this notation just to let us remember that this is not just two variables, this is three-dimensional. So this just tells me that this is three-dimensional. And so this tells me this is just two-dimensional. Okay? So we just want to make a different symbol to remind us of whether it's, because if you see this, okay, we're only talking about 2 dimensions. And if you see this, we're talking about 3 dimensions. There's a z dimension, there's an x dimension, but there must be some other dimension also. So when you see this symbol, that you're doing more than just 2 dimensions. Is that clear? Now, how did we do it? How did I find the derivative of this? Well, we said we're going to fix y at something like fix y. Here I say, let's fix y at 10. Uh-oh. I made another mistake here. This. Uh-oh. Okay. This is page 207. 207. Y equals 10 or 100. So yeah, this is a mistake. I said y is equal to 10. No, it said y is equal to 100, but I meant y is equal to 10. So this becomes 100 if we're using this equation. If y is 10, then we get this equation, right? So here I said, suppose y is equal to 100. I didn't mean that. I meant y is equal to 10. Okay? So I get this. So once I set y equal to 10 and I get this, now I can do the derivative. And then I could do the other thing, which is instead of setting y equal to 10, I could set x equal to something. And so I get dz dx and dz dx. But anyway, since we have more than 2 variables, we really want to use this symbol. Okay? More than 2 variables, so we want to use this symbol. So what do we get? If I set this equal to 10, so I get minus 100 here, then what's the derivative of this? What is dz dx in that case? What is dz dx in this case? Yeah, 2x or minus 2x. So that's easy. Very simple to do the derivative, the partial derivative. Okay, that's called the partial derivative. So we really use this notation here, and we say it's the partial derivative of z with respect to x. Then how do we do the partial derivative of z with respect to y? So then instead of setting y equal to something, some constant. We set x equal to some constant here. And then what's the derivative? Minus 2y. Okay? So then we get this result also. Now, we said that we need to put these together somehow to tell us really what's the best direction to move in. Right? We're going to take some information when we're stuck in the y plane and some other information when we're stuck in the z plane. We're going to kind of blend, we want to figure out how to blend them together to tell us really the best direction to go. Now, we're not going through all the math, but you can certainly read it in a math book. But you can prove that the best direction is a combination. Well, first of all, what do I mean by direction? Okay, so let me make one thing clear, which puzzled me for a long time. Tell me about this. First, again, let me repeat again. How many dimensions is this object, this paraboloid? 3. Okay, now here's my question. How many dimensions am I going to use to specify a direction? And this puzzled me for a long time. Well, the natural answer, would be 3. You'd say, okay, you should move like this direction or something, right? Like this direction, right? So you'd say, oh, well, you should move a certain amount in this way, a certain amount in this way, and a certain amount in that way, right? That sounds natural. But if you think about it, actually, you only need the x and y directions. So if I tell you that you're here, and I tell you you should move a little bit, let's say this is east and this is west. So I say you should move 1 meter east and 2 meters west. That tells you the direction to move. You don't need the third dimension. You only need the east-west direction to know where to move, because you're on the mountain, the other part is sort of already there. Now that bothered me for a long time. I didn't understand that. But to specify the direction, we don't need all 3 dimensions. We only need 2 of them. Actually, the third one is sort of superfluous. If we said this third one, we'd sort of be giving redundant information. So we don't need that. So we want to, now, remember, we're going to take this piece of information and this piece of information and blend them together somehow to know the best direction. So let's say that this was like, let me change these numbers. Suppose this wasn't -2. Let's suppose it was 100. And this wasn't -2, this was just 1. Now, which direction should I move in mostly in order to get the most incline? This is 100, not -2, it's 100. And this is not -2, this is 1. So should I move in the x direction primarily, or should I move in the y direction primarily to get the most change? The x direction, because when I move in the x direction, I'm going to increase by a factor of 100. But if I move in the direction of the y direction, I'm just going to increase by a factor of 1. So it seems clear that if this is much bigger, that should give us more, we should move more in that direction. But nevertheless, we still need to blend. We need to take a balance of these 2. Now, once again, in order to specify the direction, what do I have to tell? How many dimensions do I need? Just 2. I only need the x and the y. Now, here's the nice part, mathematically speaking. I'm going to specify it with a vector in the xy plane. So what do I mean by that? Let's just make sure we understand. Here's the picture again. And here we are right here, right here, right there. Now let's just draw a line down to the bottom here. Okay, I don't know where this goes really, but let's say it goes to there. Now, we said we only have to tell the east-west direction. I'm going to say, okay, let's suppose that the right direction to go, I can't draw in 3 dimensions, but I'll just try my best. We want to go in the blue direction. Let's say it turns out to be this direction. This is a vector. I want to move in that direction. I have to tell a certain amount east and a certain amount west. Well, this does that. This says move a certain amount east and a certain amount west. So what am I saying? I'm saying that a 2-dimensional vector is what I need to specify the direction. Mathematically, it's a 2-dimensional vector which will specify the direction. What direction? And this arrow tells me what direction, and I can certainly specify that as a vector, a 2-dimensional vector. So, and again, now, we need to balance the x partial derivative and the y partial derivative. We need both of those. So what is the proper balance? This is very hard to do. What is the balance? That's the question. That's the question. And the answer is this. So remember, it has to be a vector in 2 dimensions. It has to be a vector in 2 dimensions. So it has to be 1 comma there. And here's the answer. So it has to be a balance of the partials. So the answer is just this. And this you can show mathematically. You can prove that this is true. The partial of z with respect to x and the partial of z with respect to y. That is going to give you the right direction. So if this is really big, then then the primary movement is going to be in the x direction. And if this is really big, then the primary movement is going to be in the y direction. And this has a name. It's called the gradient. So, and it has a symbol. It's like that. It's the gradient of z. So what is the gradient of z? It's this. It's just all the partial derivatives. That's the gradient. And what good is it? What does it do for us? It does everything for us. What do I mean by everything? It tells us what direction to go. That's what we need to know. That's what neural networks are going to need us to know. But we are going to run into these curves, and we're going to need to get to the top or the bottom of them. That's what we're going to do. We're going to do what? We're going to calculate the gradient. And what is the gradient? It's just the combination of the partial derivatives. Okay, now you have to prove mathematically that that will give you the direction of steepest incline or steepest decline also. If you go in the opposite direction, the steepest decline. You have to prove that. So that is the idea. So we have that shown eventually. Now, suppose we had a function with a lot of variables. Now we can't graph this anymore, but we're still going to need to find minimum and maximums. And we're still going to do partial derivatives. So we can do, here's many variables. So we can do the partial with respect to x1. So what does that mean? That means you set everything else to be a constant. Everything else is set to be a constant. Now, we don't actually make up some arbitrary numbers for them to be. Like I said, suppose y was equal to 10. We don't actually do that. We just say, okay, so if I want with respect to x1, then I think of x3 as a constant, x4 as a constant, and x5 as a constant. And then so what's the derivative of this with respect to x1 if x3 is a constant? The answer is it's just x3 because suppose this was 10. So what would you say? You'd say it was 10x1. So you'd say the derivative is 10. So it's not 10, it's x3. So the derivative is x3. And then this one with respect to x1 again. So that's like 10x1 squared. So then you get this. And this one is just like a constant. The derivative of a constant just gives you plus 0. So that's how you do partial derivatives. And this is the definition. We don't use this definition, but this is the formal definition mathematically of what we mean by a partial derivative. We can get to, remember we have a chain rule, but that is only for what? that is only for 2 dimensions. That is only for 2 dimensions. But what if we have a much more complicated situation? So this is the answer for 2 dimensions. But what if we have this and we want partial derivatives? Then it's going to be more complicated. We want the chain rule, then it's going to be more complicated. Here's an example.